Hello everyone, welcome to the EasyPower Thursday webinar series. We appreciate your attendance today, and before I introduce our guest speaker, as we are in the habit of doing, we'd like to conduct a couple of poll questions just to see how the audience sizes up for the presentation that we've engaged. So if you would please participate and help us with your feedback. Obviously, there's no obligation. And so the first question we have is directly related to the topic, and that is, have you started using the updated 1584 standard? So we'll just leave this open for a couple minutes as the people are kind of coming in. We do appreciate your attendance, and we repeat this series at least a couple times a month on Thursdays from various industry experts on varying topics that pertain to electrical system analysis. So it looks like we have a consensus on this poll question. And again, thank you for participating. Here's how folks have weighed in on this. And it looks like it's fairly evenly split. All right. And the second question is basically how you fit into the equation. So if you would kind of give us some feedback there. Again, our presentation sometimes can be tailored based upon some of this information. So that's why we're sizing everybody up. No obligation. And we will have time for questions and answers as we go through the presentation. So let's close this down and share the results. Excellent. And then the third question is, what are you most concerned about as far as the standards, at least as you've been exposed to the details? And again, this is where we're going to be spending most of our time. And you're welcome to submit questions during the presentation. And I notice I misspelled my 2-second rule. Apologies. And we may not have time to cover all the questions during the presentation, but certainly any questions that are submitted, we will follow up with a Q&A email for all those that registered. All right, looks like we have a quorum here. Here's how people have weighed in. Good. I like the distribution of responses. So again, thank you very much for attending today. And I'd like to introduce our guest speaker. He's been with CIMA Plus conducting power system studies, including arc flash, protection coordination, transient recovery, and insulation coordination. And he has experience in conducting feasibility studies for the integration of renewable energy sources on existing power grids. We are very pleased to have with us today Mr. Simon Giard-Leroux. Simon, you now have control of the presentation.
Thank you, Jim. So, hi everybody. My name is Simon Giard. I'm a professional engineer, as Jim said, for CIMA Plus in Sherbrooke, Quebec, Canada. So I'd like to begin by thanking EasyPower for inviting me to host this webinar. So the title of the webinar today is the impact of the new IEEE 1584-2018 standard on arc flash studies. So basically, the IEEE 1584 is the standard that defines the equations and the methods used for calculating arc flash energy. So this has been updated about 1 year ago, and there are many differences with regards to the older version. So the webinar today, we'll start by stating our objectives for today. Then we'll go over the changes in the new version. Then I'll show you the old calculation method in the 2002 version, and then I'll show you the new method, so you're going to be able to see the differences between both. Then I'm going to show you some parameter sensitivity analyses that we've performed for the new standard. Then we're going to end with conclusion and then a question period. So the objectives for this webinar today. So I hope that by the end of this webinar, you should be able to know what steps are required to perform arc flash calculations. So how the parameters are used in the equations. Know the differences between the old 2002 version and the new 2018 version. And also know a bit the impact of the parameters on the incident energy. So, for example, the voltage, how it impacts the energy, how the enclosure size, so width, depth, and height of the enclosure, how it affects the energy, the electrode configuration, the electrode gap, which is the distance between the phases, the fault current, and the working distance. So let's begin by stating the changes. So for the Canadian listeners, the CSA Z462 is the safety standard in Canada, and it refers to the IEEE 1584 for its method of calculating arc flash. So basically, IEEE 1584 is an international standard for arc flash studies, and a bunch of local standards refer to it. So it's the first update since 2002. There's been some amendments back in 2004 and 2011, but it's been a long time since there was no new version. So it took about 16 years for the IEEE to come up with new equations to better represent the arc flash phenomenon. So the equations in the IEEE standard are basically empirical. So they're not based on theoretical equations, they're based on test data. So basically in the 2002 version, the equations were based on about 300 tests, but now in the 2018 version, it's about 2,000 tests that were used, and then statistics were applied to come up with the equations. So big change in the new standard is the new concept called electrode configuration. So what is meant by electrode is the bus bars, it's the light conductors. So this is now used as a parameter. It wasn't in the past. So you have 5 configurations: VCB, VCBB, HCB, VOA, HOA. So I will go through examples of each one and how to determine which ones apply to you. And now also you have a big changes. The enclosure size of the equipment is now used in the calculations. So the height, the width, and the depth of the cell of the equipment or the panel enclosure. So the application limits were a bit extended compared to the 2002 version. So the 2002 version, you had, well, the voltage has not changed. So the IEEE 1584 still applies from 208 to 15 kV, 3-phase only. The short circuit currents lower limit has been lowered to 200 amps. And it goes up to 106 kA, and the distance between phases has been extended too. So the application of the standard now covers more cases than before. So in the 2002 version, the grounding of the system was a parameter. So whether or not you were delta, floating Y grounded, it had an impact on the energy. But the IEEE, when they did their tests, they saw that the grounding didn't have an impact in the end. So they removed this as an input parameter in the equations. Now there's a concept that's called the 2-second limit. So basically, as a basic reminder of arc flash, you have the energy which is proportional to the fault current squared times the fault clearing time. So the fault clearing time, it's the time that it takes for the upstream protection to clear the fault and stop the arc flash. So there was something called the 2-second limit, which means that within 2 seconds, you consider that the worker has time to go back and move away from the source of the arc flash. So the worker is not subject to the arc flash for, let's say, 1,000 seconds. If the protection takes 1,000 seconds to trip, you don't write the energy for 1,000 seconds because it's unbelievably high, and the worker will have time within 1,000 seconds to move away. So there was a 2-second limit. It doesn't apply in bucket trucks, for example, or areas with restricted space. So it's been maintained. So the 2-second limit is still there, but you have to be careful that it only applies when you have enough space to move away. So if it's in a bucket truck, it doesn't apply, for example. So a big change is there was in the 2002 version, there was a cutout point at which your distribution is so low power that you stopped needing arc flash studies. So the past version, the exception was if your equipment is below 240 and it's fed by a transformer larger than 125 kVA. But now it's been changed. So now it's still under 240 volts, but instead of transformer size, it's now available short circuit current of 2 kA, so 2000 amp of fault current. So let's say we're trying to find the equivalent of the 2 kA in transformer size. So let's say we have a 480 to 280 volt transformer that has an infinite source above it and that has an impedance of 4%. So what would be the size of the transformer that we could say is the cutoff limit with the new 2 kA? The formula is pretty simple. It's square root of 3 times 208 times 2 kA times 4%. So it comes up to about 29 kVA. So as you see before, it was 125 kVA. Now if you convert it to equivalent transformer, it's 29 kVA. So you go much further down in your distribution. So the arc flash studies, they need to be updated to include all the low power equipment. So there was a concept called the motor size limit. So basically, in the 2002 version, it only said to consider more motors that were larger than 50 HP. So the 50 HP text has been removed from the standard. It only refers now to large motors, but doesn't give a rating in horsepower or in kilowatts. So it still says large motors, and then the new standard refers to IEEE 1584.1 that still has the 50 HP limit. It refers to the Violet book that still has the 50 HP limit, and it refers to the C37.010, which still considers the 50 HP. So all in all, they removed the text, but all the references still say it's 50 HP. So this, we consider it that it has been maintained. So what about arc flash for high voltage? So basically the IEEE, the last version, the 2002 version, said that above 15 kV, the Lee method was recommended. So the Lee method is a pretty simple calculation, and it gives very conservative results. So instead of stating use the Lee method, they remove the Lee method from the standard, and then they say there are alternative ways. We don't recommend any one of them. So it gives more space to software solutions, other software solutions that can do high voltage arc flash, for example. So what about single phase systems? So that was a big issue for some clients. So there's single phase systems. How do we model them? How do we calculate them? The 2002 version was pretty straight simple on that. It said they're not included. That's it. But now what they say in the 2018 version is it doesn't cover it, but you can use the equations with the line to neutral voltage and the line to ground fault current, and it will give you conservative results, but still it says that it's usable. So it gives a bit of indication of how to do arc flash for single-phase systems. Then for DC networks, what they said in the last standard was they're not included. That's it. So now what they say is they refer to some white papers that were published in the IEEE journals. So you have, for example, the Doan method, which can be applied. So the IEEE 1584 gives some methods that can be used for DC now. So let's start by showing you the old equations in the 2002 version. So the method itself, so you start by finding your arcing current. So basically, the first step of an arc flash study is you draw your time current curves, you calculate your fault current, and then this is what was applied before. So first, calculate your arcing current. Then you put your arcing current on the time current curve. You find your trip time. Then you calculate your normalized energy. Then you denormalize your energy with the working distance and the arc fault duration. Then you find the arc flash boundary. And then if you're below 1 kV, you need to do a second arcing current, which is equal to 85% the arcing current. And then you calculate the energy with that one. And in some cases it's larger. Sometimes it's smaller than the original arcing current. And then you choose the biggest, the largest value between the two. So the equations, for example, you have as an input the K factor, which says open box, open configuration, or inside a box. You had your fault current, you had the voltage, you had the distance between the phases, so the gap. So you plug that in a logarithmic equation, then you say 10 to the log IA, and then you get your arcing current. So you take your arcing current. So the way you read this is basically the x-axis is the time. The x-axis is the current, and the y-axis is the time. So what you do is you go on the x-axis, you take your arcing current, you draw a little arrow here, and then you go up, 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 and then you hit the second, the right side of the fuse curve. So this is the total clearing time of the fuse, and then you go to the left or to the right, and you find your arc fault duration with this time current curve. So once you have your time and your arcing current, you can calculate your normalized energy. So this formula was two factors, so K1, K2, and G, and then you get your normalized energy, and then you denormalize your energy using some factors, and you put your arcing time, you put your working distance, and there you go, you have your energy in calories per centimeter squared. And then for the arc flash boundary, it was this formula. So the arc flash boundary, as a reminder, is the distance at which you need to go back from the source of the arc flash for the energy to drop at 1.2 calories. So 1.2 calories is equivalent with PPE 0 category, which means basic workers equipment in an electrical room. So hard hat, safety glasses, long sleeve natural fiber clothing, for example, and protection shoes. So these were the equations in the past version. So you see the equations were pretty simple, pretty straightforward. So the new equations now. So the new method. So it's still about the same method. So you find your arcing current. Then to find your arcing current, you need to specify your electrode configuration. Then you calculate your arcing current. Then you find your fault duration with the time current curve. So, for example, EasyPower does this automatically for you. So the incident energy, then you calculate it using a bunch of equations. Then you calculate your arc flash boundary with some other equations. And then you need to do a minimum arcing current. So in the last standard, the minimum arcing current was always 85%, and it was only required under 1 kV. Now, in the new version, it's required for any voltage, and it's not 85% anymore. So it can vary depending on voltage. So the IARC min can be, for example, 90% of the IARC. It can be 70% of the IARC. So it can vary with voltage now. So it's a bit more complex. So the first step is to determine the electrode configuration. So what is that? So electrode configuration basically is, remember that the electrodes are the live conductors. There's the bus bars, there's the cable extremities that are unskinned that show live conductors. So basically, for example, if you have a short circuit below a breaker here in this cell in the top right, if there's a short circuit there, the arc flash will go down in the box. So it won't go perpendicularly towards the worker. It will go down. So this is what we call VCB, vertical conductors inside a box. So this represents an arc flash going down inside a cell. So let's say VCBB. So it's the same as VCB, vertical conductor inside a box, but it's also terminated in an insulating barrier. So what's an insulating barrier? So for example, if you have the top of a breaker, this is a molded case circuit breaker. So the top of it is in plastic, and if you have a fault above the breaker, the source of the fault current will come from the upstream cable, and then the arc flash will be diverted towards the worker. It will like flatten on top of the breaker, and it will be pushed towards the worker perpendicularly to the panel. So in this case, the arc flash doesn't go down inside the cell. It goes, it's kind of flattened towards the person. So in this case, the arc flash, the arc that the person, the energy that the person is gonna get on himself is gonna be higher in VCBB than in VCB. Then the worst scenario inside the box is HCB, which means horizontal conductors inside the box. So basically, if you have a fuse that's held in with lugs, the lugs act as electrodes that basically push the arc flash directly towards the worker. So this is the worst case in that case. So from worse to less worse in most cases, you have HCB, then you have VCBB, and then you have VCB. So VCBB can only exist when you have a breaker. So if your equipment has fuses, you cannot use VCBB, right? So HCB, then you have two electrode configurations, but these are for open air equipment. So VOA means vertical conductors in open air, and HOA, horizontal conductors in open air. So basically the same thing. So basically electrode configuration, it's where does the arc go when there's a fault? Does it go towards the worker or a bit off? So this is what it represents. So once you have the electrode configuration, you need to calculate if your voltage is above 600 volts, you have three arcing currents to calculate first. So you have IARC 600, you have IARC 2700, and you have IARC 14.3 kV. So you always calculate three arcing currents with this big equation. So it's much more complex than the 2002 version. So you have a bunch of K factors. So K4, K5, K6. These are based on your electrode configuration. So these will change based on your electrode configuration. And then once you have these three IARCs, so IARC 600, IARC 2700, and IARC 14300, then you need to interpolate these values. So you need to calculate IARC 1, IARC 2, and IARC 3, and then your final value, your final IARC, if your between 600 and 2.7 kV, it's IR3. If you're above 2.7 kV, it's IR2. So you see, to find the IR, it's at least 6 equations instead of 1. Now, so if your voltage is below or equal 600 volt, it's much simpler. It's only 2 formulas. So you have the IR 600 to calculate with a bunch of factors, and then you find your IR final with this small equation here. So again, even if it's simpler, below 600 volt, it's still more complex than the 2002 version. So once you have your IR, same thing, you go on the time current curve, you put your fault current on the x-axis, then you go up, you go to your total clearing time, and then you go sideways, and then you find your fault clearing time. So now, as I stated before, the new standard has enclosure size now in its equations. So the enclosure size, height, width, and depth, if your voltage is below 600 volts, and your height is below 20 inch, and your width is below 20 inch, and your depth is below or equal 8 inch, your box is considered shallow. So this will affect the results. If your box is considered shallow, if it respects these 4 criteria, it has an impact on the results. And if it's not shallow, then it's typical. So you take your width, you take your height, you take your voltage, and you calculate a few factors here, and then you find the equivalent enclosure size ratio, and then you find your enclosure size correction factor. If it's shallow, it's this formula. If it's typical, it's this formula. Then this is the big equation. So you need to calculate 3 energies, one at 600 volts, one at 2700 volts, and one at 14.3 kV. So regardless of your actual voltage, you need to calculate all of these. So if you're at 480 volts, well, this is a bad example because it's above 600 volts, these equations only. So let's say you're at 4.16 kV. You need to calculate energy at 600, energy at 2700, and energy at 14.3 kV still. So in these big formulas, you need to put your fault time. You need to put your distance between the conductors. You need your arcing currents from the other equations that we saw before. You need your voltage fault current. You need your distance, your working distance. You need your correction factor for the enclosure size that you calculated before. And you need the coefficients K that come from some tables, and they're dependent on your electrode configurations. So once you have the 3 energies calculated, then you need to interpolate them with the calculating E1, E2, E3, and then your final energy. If you're below 2.7 kV, it's E3. If you're above 2.7 kV, it's E2. And then all these equations are in joules per centimeter squared, but if you want to convert it to calories, you just divide your result by 4.184, because there's that's the conversion factor for joules and calories. So that was energy above 600 volt. But now if you're below 600 volt, the equation is simpler. You don't have to calculate 3. You only have to calculate 1. So energy, you need to put your fault current, you need to put your arc time, you need to put your distance between phases, you need to put your working distance, correction factor, K factors, so the same parameters, and then your final energy is just that value. So this is the biggest equation of them all. So this is the equation for the arc/boundary. So it's 10 to the this big fraction. So you need to put you need to calculate three interpolation, three arc flash boundaries. So at 600, at 2700, at 14.2 kV, with your arcing currents, your gap distance, your fault current, your enclosure size, your arc duration, and then you need to interpolate again, find AFB1, AFB2, AFB3, and then your final arc flash boundary. If you're below 2.7 kV, it's AFB3, and if you're above 2.7 kV, it's AFB2. When you're below or equal 600 volt, the equation is simpler. You don't need to calculate 3, you only need to calculate 1. So it's this equation here, and your final arc flash boundary, it's directly this value. Now, so you have your energy for the maximum arc current, but now you need to find the minimum arc current. So it's like a second iteration. So to find your I arc min, you multiply your I arc by 1 minus 0.5 times var CF. So var CF, it's the 85% that we talked about earlier. So it varies depending on the voltage. And then you get your minimum arc current, then you find your the arc time with this one, you find your energy with this one, you find your arc flash boundary with this one, and then your final incident energy is the highest value between the one for I arc and the one for I arc min, and then same for your arc flash boundary. So these are the these basically are the all the equations in the new standards. So the method has been very much complexified. And now the new, EasyPower uses these new equations, so they're automatically built in. But this is as a way to show you what's going on behind the magic in EasyPower. So now I'm going to show you some sensitivity analysis. So as you see, the equations they're very complex. So it's hard to predict what's going to be the impact of varying some parameters on the energy at the end. So what if I vary the height a little bit? What if I vary the width? What if I vary the gap or the working distance? What's the impact? You know, you can't isolate the variables in the equations I showed you. It's too complex. So I prepared a tool in Python to do sensitivity analyses for IEEE 1584 2018. So this uses numerical methods to find the impact of all the parameters on the final energy. So I'm going to show you some examples and some curves of the impact. So I'm going to show you some examples that cover basically all that's within the standards. So typical cases for 15 kV switchgear, 600 volt switchgear, 208 volt panel, which is shallow. I'm going to show you the difference between shallow and unshallow. And then 15 kV outdoor breaker, for example. So let's say we start by a 15 kV breaker, 15 kV switchgear. So you have the lower section here, which has the relays, and you have the upper section here that has the draw-out breakers, for example. So let's say your upstream protection trips in 2 seconds. So the 2-second rule, if it's the point of connection with the utility. So for example, if you have a factory that's fed at 15 kV and you have the point of connection, you never know when the utility changes their protections. If they change their relay settings, if they change their fuse type, they won't tell you. So you should always use 2 seconds on the main equipment of your facility. So let's say you always have 2 seconds because it's the main equipment of your facility. So let's say we put typical values for 15 kV switchgear with a fault current of 10 kA, working distance of 36 inch. What's the impact of the voltage on the energy? So the energy is the y-axis and the voltage is the x-axis. So you have the blue curve, which is VCB. You have the orange curve is VCBB. You have green curve is HCB, and then you have the old version of the standard in red. So what's the difference between all of them? So you see HCB for any voltage is much higher than VCBB and VCB. And you see the old version of the standard it's about in the middle. But you see some discontinuity here in the green curve. So there's like a spike here. It's because these equations are not made to be continuously graphed. You know, there's an equation above 600 or below 600. So that's why there's like some glitches in the equations here. So let's say we vary the voltage. That's the impact on the energy. So let's say we fix the voltage back to 13.8 kV, and now we vary the height. What's the impact of the height? So you see, the worst case energy is always when your height is smaller. So when your height goes up, your energy goes down. So, and if you look at the curve of the 2002 version, it's flat. Why is it flat? Because it's not a parameter in the equation. So that's why it's flat. But the other ones, we see it varies, but it doesn't vary so much. So you see the VCBB, for example, it says at 44 and then drops to 38. You know, it's not a significant drop. So it's about the same for the width. So the energy is higher when your width is lower, and then the energy goes down if your width goes up a little bit. And then the old version stays the same. So the depth has absolutely no impact on the energy in this case, because it's not a shallow box. It cannot be shallow. So to be shallow, it has to be under 600 volt, height below 20 inch, width below 20 inch, depth below or equal 8 inch. And in this case, it's never the case because you're at 15 kV, so the depth has absolutely no impact. What about the gap? Well, the gap has a big impact. So the gap, it's when your gap is lower, your energy is lower. And if your gap goes up, your energy goes up. And then you can see here, HCB is still worse, VCBB then. And then the IEEE and the VCB have a bit of a similar curve shape here. Then this is the big one. So the fault current. So when you plot your energy against your fault current, what you see here is that about 50 kA you have your peak for HCB, but your peak for other configurations are much higher. So if your fault current is, let's say, below 70 kA, then your HCB would be higher, but then your HCB would be lower. So this is a bit of an interesting result here. So normally when you do arc flash study, you try to find the worst case incident energy by varying your scenarios. So you see, for example, low fault current, medium fault current, high fault current, generator, and then you put a few points, and then you try to find your worst. But in this case, you can see the actual worst is exactly at this value. And then your working distance, it's an inverse square law. So the more you move away from the source of the arc, the more the energy drops. So now example 2, if you have a 600 volt switchgear, what's going to be the impact? So now there's no 2-second rule. Now I've used a Ferrous Shawmut AGT 600 amp fuse. So you have to consider that the arcing current changes for every point on these curves. So the trip time will change also. So let's say we have the voltage plotted here. So it's about the same relationship, but since our actual voltage is 600, then it's hard to say with all these lines going up and down. It's hard to say what's worse. So let's look at other parameters. So let's say your height. Your height doesn't have that much impact. So you see it goes from above 1.2 to below 1.2. So it's not that much. But still, if you're above 1.2, you need more PPE to do live work than if you're below 1.2. So your height can have an impact of on what PPE so PPE is personal protective equipment. So it can have an impact on if you need a face shield or not, or something like that. So still, your worst case energy is lower height, and it goes down when you increase the height. Same thing with the width, absolutely the same. And then it's the depth. Well, it cannot be shallow because it's equal to 600 volts. So to be shallow, it has to be lower than 600 volts. So in this case, it cannot be shallow. So that's why depth has absolutely no impact. And then electrode gap. So you see here, the last standard had a bit of a jump here with the electrode gap, but this is due to the electrode gap only went up to 150 millimeter in the last version. So now the standard goes up to 250 millimeter, but the past equations didn't go up there. So this is why you see a peak here, but it doesn't really apply because the model didn't go up to above 150 millimeters. So this part of the red curve should not be shown because the past equations were not valid. So here you see your worst case is very, very higher for HCB. Then you have the old version of the standard. So the HCB would give you 50 calories. The old standard would give you 20 calories. VCBB is about the same. Then you go down, it's VCB at about 15. And you see your worst case is really at about 5K in that case. And then you see the working distance. What's the impact? So the working distance is still the same as the inverse square law. So third example, so let's say we have a shallow panel this time. So what's the impact? We're gonna see the impact of the depth on this one. So the 208 volt panel. So if we plot the voltage, we can see here, so it's, there's no 2-second rule this time. It's protected by a Merson TRS-R 100 amp fuse. So let's say we have a voltage here. So you see the HCB is always the highest. And then there's some overlap here between the DCB, VCBB, and the last standard. So it hasn't changed much unless it's HCB. If it's HCB, it has changed a lot. So HCB again is very, very higher when you have a shallow 200 volt panel. So in this case, your enclosure height will have a big impact if you're HCB, but if you're VCBB and VCB, it's much lower. So this is the width, so it's about the same as the height. And then your depth. So this is where your depth has an impact. So if your box is shallow, so if your enclosure depth is below 200 millimeter, this is 8 inch. So your energy will be lower if it's shallow. Then if it's higher, then it becomes typical and your energy increases a little bit. So in this case, electrode gap, still the HCB is very, very high. The other three, the past standard and the VCB, VCBB are about the same. Now, it's interesting to see that for the fault current, the peak value is not at the same place anymore. So in the last standard, the red curve, the peak was at about, let's say 1 kA, and now it's at above 2 kA, like 2.2 kA now. So it's interesting to see that the peak is not at the same place anymore, and it's interesting to see the impact of the electrode configuration. You see the HCB is very, very, very high. It reaches up to 12 instead of 3 calories. And then your working distance here, it's about the same as the other ones. So it's an inverse square law. So now the last example. So it's a 15 kV breaker, which is outdoors. So here I've used VOA HOA electrodes, and the Lee method. So just to show you how the Lee method is conservative, you see here the Lee method goes way up. And then you have HOA, you have VOA, and then you have the old method. So the old method is lower energy than the new method, but then you have Lee, which goes a step above. So now in this one, the 2-second rule is applied. So if you plot it against so in this case, there's no like enclosure height, width, or depth because you're open air, so there's no box. So here you can see the electrode gap has no impact on the Lee method because it's not a parameter, and then you don't see much variation here with the electrode gap in the old equations. So both with full current, you see the Lee method basically is a 45-degree angle that goes up to 400 calories. But the other, the old and the new method, they're basically about in the same range. And then the working distance, well, it's the same. So the Lee method goes up to 4,000 calories in that case. If you're really close to the arc, it goes up to 4,000. So let's finish with some conclusions and recommendations. So the calculation method, as you can see, is very different between the 2002 and 2018 versions. It's difficult at first glance to predict the impact of the update on the incident energy because the equations are very complex. So the electrode configurations and enclosure size are parameters in the equations now. You need to go much further down in the distribution to consider everything with the new standards. So the 125 kVA exception has been replaced, so you need to go much further down up to around 30 kVA transformers. The 2-second rule still applies, and then the results are very different, as you could see on the curves. So I recommend that your R flash studies should be updated to the new version to ensure the safety of the workers. So is there any questions? You can submit them through the question box. Thank you for your assistance.
Thank you, Simon. There are a number of questions. So let me kind of go through the ones that are top of the list here and see if you can answer them.
Yep.
All right, so the first one that comes in is says, what incident energy and arc flash boundary shall be labeled on the equipment that's 240 volts nominal or less with less than 2000 amp short circuit current?
Well, in this case, there's not enough energy to sustain an arc. So the arc flash danger is not really present. So what I would do in this case is put a shock label only. So you would put a shock hazard label with a danger sign. You would put the limited approach boundary. You would put the restricted approach boundary and the glove class only.
Okay. Next question. How will tables in 70E be affected by the new calculation method, particularly for troubleshooting equipment under 600 volts?
The 70E table will be updated in the next version to consider this. So basically, the tables, you had a column that said the maneuver, and you had a table that said the PPE requirements. So these will be updated in the new NEC, the new NFP.
Okay. What is the electrode configuration if fuses are being used? And I'm sure this is from Daniel. I'm sure he was referring to a specific image that you were looking at.
Yeah. So I'll go back to the image. So basically, so if you have fuses, there's no breaker to act as an insulating barrier. So VCBB does not apply. And VCB does not apply either. So when you have fuses, I would suggest using HCB because the lugs that are holding the fuse will act as horizontal electrodes that will push the arc flash towards the worker.
It works for me. So this is from Joven. He says, can you explain how to consider electrode configuration for a fusible disconnect switch with fuse in an MCC bucket? I think the question goes to, can there be multiple configurations?
Well, in a case of a MCC cell with fuses, what I would do is pick HCB. So HCB in all cases will be higher than VCB and VCDB. So what I would do is consider HCB for MCCs with fuses.
For areas that I'm contracted to perform an arc flash, but I don't know the electrode configuration for the enclosure size, what would you recommend?
If your equipment has fuses inside, I would recommend using HCB. If your equipment has breakers, low voltage breakers inside, I would recommend VCDB and VCD. And then if you're working on some transformer terminals or some bus bars, rectangular bus bars, for example, then I would recommend HCB because they will act as horizontal electrodes. And for the enclosure size, what I would recommend is going to the IEEE 1584/2018 the tables. There's an appendix with some tables with some typical enclosure sizes, so these can be used. And also the EasyPower library has some equipment sizes inside, so these vary depending on the equipment type you use in your bus in EasyPower. So I would recommend using this, but just state to the client that you use typical values and the results should be interpreted with care.
All right. So this is interesting. The question is, for enclosure size, do you mean circuit breaker enclosure size, or what's the definition of enclosure?
So the enclosure is the box, the cell that contains the breaker and the cables entering the breaker and the cables leaving. So, for example, in the figure you're seeing now, you have the cell. So for example, if it's a MCC, it's the MCC cubicle, it's the MCC cell, it's the MCC bucket. If you have a switchgear, it's the cell of the breaker container when you rack out your breaker. If you're working in a 480 volt panel, it's the panel size. So it's what's the area inside which the arc will propagate from.
I like it. All right, so the next one, which is the method to work or use over 15 kV from the point of view of the standard and from EasyPower?
So, in my opinion, if you're just above 15 kV, if you're let's say up to 25 kV, the Lee method is pretty appropriate. There are some other software that can be used for voltage above 15 kV. Or I don't know, Jim, do you have some comment on that from the opinion from EasyPower?
I do. For open air faults, there's a choice or a selection in EasyPower that is actually similar to the results you get with ArcPro. And we've gone to great pains to actually verify plot for plot how that tracks the ArcPro results. In the tool, you also have the ability to select the Lee equations for something that's not open air. So I think that's the only recommendation from EasyPower. So the next question is, how are arc flash results comparing the new standard to the old one? I think you did a pretty good job. So is there a general rule of thumb, or do you need to go through each?
It's hard to say because it depends on your protection. It depends on all parameters. it's very hard to predict. So I gave some general cases, but it's going to be hard to predict. Yeah.
Yeah, fair enough. Some of this you may have answered because it was entered real time. Is the shallow versus typical cutoff voltage less than 600 volts or less than or equal to 600 volts?
It's less than 600 volts. I'm just going to show you. Yeah, it's below 600 volts.
All right.
When you're equal 600, it doesn't apply.
Okay, so this is from David, and it's regarding single-phase systems, 2400 volts, 2500 kVA. It appears I can model this and perform arc flash calculations using three-phase formulas. From what you say, I'm not sure I'm comfortable with this. And let me finish. My guess is that you're typically looking at 120/240 panel boards with much lower transformers. Any thought about dealing with large single-phase systems?
Well, with large single-phase systems, you can model them as three-phase systems and use the same equations. For example, in EasyPower, you can use your line-to-line voltage, and you will get conservative results, of course.
Fair enough. Are there many changes where the incident energy is roughly the same? And I'm not sure if that's a follow-on question. Can't tell.
Well, it's a bit hard to tell. What I've seen is I've done some comparisons with past studies and new studies, and what I've seen is at low voltages, the energy can go down a bit, and at medium voltage, it can go up a lot. This is what I've seen.
All right. This is from Jeremy. He says, don't most of the changes allow for a lower cal rating? In most cases, isn't EasyPower's default settings the most conservative? From a company liability aspect and personal safety, why would we not just use the most conservative values? Example, the default results in 13 calorie, and by changing the electrode configuration, it results in lower than 12 calories. Why would we not just use the 13 calorie value?
So basically, when we do an arc flash study, we always try to we take the worst case, but that is reasonable, because if you go worst case, you could use 1,000 seconds, you could use 100K, but you'd get very, very large results that don't represent reality. So what we try to do when we do our flash calculations is find something that represents reality, and the objective is not to go full PPE gear all the time in any situation. So what happens is when workers use let's say 40 cal PPE, they wear a big suit, a big helmet. There's low visibility. There's low dexterity. There's more chance that they can injure themselves or do a bad maneuver, or they don't like working with these. So we don't say, it would be simple to say that the energy is very, very high everywhere and consider the worst case, but we don't. We need to make sure that it represents the reality, and but at the same time show worst case results too.
All right. This is a question from Barry. He says, example 1 was stated that the 2-second rule should always be applied at the utility incoming location due to relay times possibly changing at the serving utility. Is the 2-second time to be used on utility incoming location when below 15 kV? For example, at a 600 volt switchgear location?
Yes. So when we do, for example, a small factory that has a 25 kV to 600 volt transformer, and we check the incident energy on the main breaker of the 600 volt switchgear, we always put 2 seconds, because the utility can change their fuse, their fuse that upstream the transformer anytime they want, and they can put a fuse that's slower than the one in your study, and then your R slash label doesn't work anymore. So that's why we use 2 seconds.
Let me ask an additional question. Do any utility companies in your experience provide trip times for a worst case fault that they can support?
Well, basically, they give you curves for their fuses and their relay settings, but they don't normally give you a maximum value. But the 2 seconds, it's because the worker has time to go away from the arc flash.
Right. Okay. This one from Richard. Considering electrical distribution system that's not barriered between sections, when calculating the incident energy at the line side of the main, do you use the main cubicle dimensions or the dimensions of the entire lineup?
Well, normally if there's a separate cell for the main breaker, and then there's an enclosure for the feeder breakers, you need to put a bus upstream of your main breaker, and then the energy on that one would exclude the main breaker in its arc flash calculations. So you'd have a label on the main breaker, and then your main breaker can be considered for the arc flash on the feeder breakers. And if they're all in a single large enclosure, then the large enclosure would be the size, the only size that you put inside EasyPower.
So we're only about halfway through the list of questions. I'm thinking we may need to cut this off and answer the balance via email or Q&A page. But I do have one more question that actually bothers me, and it's reminded by the question from Richard. Said the incident energy, for less than 2 kiloamps and 240 volts, what stickers do you put on? I think you explained that. But since there's no category 0 or no indication of what to do for less than 1.2 calories, if I calculate 1.2 calories or less, what should my sticker say? Right? If I calculated instant energy.
In the case that you're below 240 and below 2K?
No. So say I'm 480, but I've calculated less than 1.2 calories exposure.
So you should put that energy on the label?
That's the way I feel about it.
Yeah.
All right. Thank you, everyone, for attending. Certainly, you're welcome to contact Simon if you have additional questions, and we will be distributing the list of all the questions with the Q&A for everyone that attended today. Simon, I appreciate the effort. It was a very good presentation, and I hope everyone has a good day.
Thank you very much, and thanks again to EasyPower for inviting me to host this webinar.
So long.